Good morning, students. Today our topic is vapor pressure of liquid solutions. So liquid in liquid. And here let us consider a binary solution contain component 1 and component 2. Binary solution means the solution which is contain two components is called binary solution. So there are two components, component 1 and component 2. And these two components are volatile components. Volatile means the components which are easily evaporate are called volatile components. For example, diesel, petrol, kerosene. So all these are the volatile components because even at a room temperature they can evaporate. So diesel and petrol are highly volatile components. So here I am taking a closed vessel. So in that closed vessel I am taking two components, component 1 and component 2. So these two components are volatile component. So let me take one closed vessel. This is the closed vessel. In that closed vessel I am taking two components, component 1 and component 2. The component 1 color is blue color and the component 2 color is red color. So I'm taking two components and these two components are in liquid state because here we are taking the vapor pressure of liquid in liquid solution. So this is the solution, liquid in liquid solution. So both are liquid components, component 1 and component 2 both are liquid components. So this is the solution and these two components are volatile components, volatile. And here this is the liquid phase. So this is the solution and these two are volatile components now. So that's why they are evaporated, then they are converted into gases. So that solution also we have that two components, component 1 and component 2, but they are in gaseous state. So here the equilibrium will be established between the liquid phase and gaseous phase. Means how many the liquid particles are converted into the gas particles, the same number of gas particles also be converted into liquid state. And here the pressure will be established. So at equilibrium the total vapor pressure is P total, the total vapor pressure of component 1 and vapor pressure of component 2 is called total vapor pressure. So that total vapor pressure is represented by P total, and the partial pressures, the individual component pressure is called partial pressures, and the partial pressures of component 1 and component 2. So the component 1 partial pressure is P1 and the component 2 partial pressure is P2, and that partial pressures related to the mole fractions. So for component 1 the mole fraction is x1, and for component 2 the mole fraction is x2. Component 1 mole fraction x1 and component 2 mole fraction x2. And the French chemist Francis Mort Rolt in 1886 gave a quantitative relationship between the partial pressure and mole fraction. So this relationship is known as Raoult's law. Raoult's law. The Raoult's law statement is, for a solution of volatile liquids, the partial vapor pressure of each component is directly proportional to its mole fraction present in the solution. And let me take that component 1 and for component 2. For component 1, P1 partial pressure is directly proportional to mole fraction of component 1. And here let me take one constant P1 is equal to the constant P1 naught and x1. Then for component 2, the component 2 partial pressure is directly proportional to mole fraction of component 2. And here let me take one constant P2 is equal to P2 naught x2. So here P1 naught and P2 naught are vapor pressure of pure components. Pure components vapor pressure. Vapor pressures. Pure component means the component which is not mixed with another component, that is called pure component. For example, here I am taking two components, component 1 and component 2. So if I take in a beaker, I am taking only component 1, so that is called pure component. In another beaker, I am taking component 2, so that is called pure component. If I mix both in one beaker, so then that component 1 and component 2 are not called pure components. So these are the vapor pressures of pure components at same temperature. So the temperature is same. And according to Dalton's law of partial pressure, the total pressure over the solution phase will be the sum of the partial pressures of all the components. And we know that Dalton's law, already we studied that Dalton's law in states of matter. So that Dalton's law, So the total pressure exerted by the mixture of gases is equal to the sum of the partial pressures of the individual gases. This is known as Dalton's law. Already we studied that Dalton's law in states of matter. So according to that Dalton's law, P total is equal to P1 plus P2 and is equal to P1 is equal to P1 naught into x1 plus P2. P2 means component 2 partial pressure, P2 naught x2. P2 naught x2 and is equal to, and we know that sum of mole fractions is unity, means x1 plus x2 is equal to 1. So then we can write that x1 is equal to 1 minus x2. This x2 comes to here, minus x2. So instead of x1 we can write that 1 minus x2. So here P1 naught into 1 minus x2 and plus P2 naught x2. P1 naught into 1, P1 naught minus P1 naught into x2, P1 naught x2 or x2 P1 naught, and plus P2 not x2 is equal to, or we can write that P1 not and plus this one P2 not x2, and this is the minus now, so minus P1 not x2. So P total is equal to P1 naught plus, and we can take that common x2. x2 is the common, so x2 into P2 naught minus P1 naught. P2 naught minus P1 naught. So P total is equal to P1 naught plus x2 into P2 naught minus P1 naught. So this is the formula for P total. P total is equal to P1 naught plus x2 into P2 naught minus P1 naught. For binary solutions, the P total is equal to P1 naught plus x2 into P2 naught minus P1 naught. So here P total is equal to P naught 1 plus x2 P naught 2 minus P naught 1. So here the conclusions, number 1, the total vapor pressure over that solution can be related to the mole fraction of any one component. So the total pressure P total is related to any one component mole fraction. Any one component mole fraction. And number 2, the total vapor pressure over that solution. So here this is the solution. So over that solution, the total vapor pressure over that solution varies linearly with the mole fraction of component 2. Mole fraction of component 2. Mole fraction of component 2. And third one, the total vapor pressure over that solution decrease or increase with the increase of mole fraction of component 1. With the increasing of mole fraction of component 1. Mole fraction of component 1. Now let me take a plot of vapor pressure versus mole fraction. Vapor pressure and mole fraction. So this is the plot of vapor pressure and mole fraction. So this is the y-axis and x-axis. On y-axis we are taking the vapor pressure. On x-axis we are taking the mole fraction. So this is the first line. So this first line indicate that for component 1. This is the first line. The first line is for component 1. So this is the partial pressure of component 1. And this second line, the red line, is for component 2. Partial pressure of component 2. And here this line is for total pressure, total vapor pressure, means component 1 partial pressure and component 2 partial pressure. And this is the third one. So first one for component 1 and second one for component 2 and third one for total vapor pressure. And here the component 1 mole fraction x1 is equal to 1 and component 2 mole fraction x2 is equal to 0, because we know that sum of mole fractions is unity. So component 1 mole fraction 1, so then the component 2 mole fraction 0. And here the component 1 mole fraction 0 and the component 2 mole fraction is 1. So if you go from left to right, the component 1 mole fraction gradually decreases. If you go from right to left, the component 2 mole fraction gradually decreases. So if you go from left to right, the component mole fraction gradually decreases as that component 2 mole fraction increases. If you go from right to left, the component 2 mole fraction gradually decreases as that component 1 mole fraction increases. If I take a middle point, so there is a half of the mole fraction of component 1 and component 2. Component 1 mole fraction 0.5 and component 2 mole fraction also 0.5. So if I take this point, so at this point the component 1 mole fraction is more than the component 2 mole fraction. For example, the component 1 mole fraction is let me assume that 0.8 at this point. Then the component 2 mole fraction is 0.2. If I take this point, so at this point if you go from left to right, the mole fraction of component 2 increases. So here the mole fraction of second component is more. So at this point the component 2 mole fraction, let me assume that 0.9, then the component 1 mole fraction is 0.1. So here we are taking two components, component 1 and component 2, and both are volatile components. So let me assume that the component 1 is less volatile than the component 2, means the component 1 evaporate fastly than the component 2. So here component 1 less volatile, component 1 less volatile, and component 2 high volatile. So then the component 1 pure vapor pressure P01 is less than the component 2 pure vapor pressure, because the component 2 is the high volatile. The component 2 is a high volatile. So here P1 naught is a pure vapor pressure of component 1 and P2 naught is a pure vapor pressure of component 2, and P1 is the component 1 partial pressure, P2 is the component 2 partial pressure. And here a plot of P1 or P2. So this is the P1 and this one is the P2. So line 1 and line 2. So a plot of P1 or P2 versus mole fraction of x1 and x2 will give the linear plots. So these are the linear plots. or linear lines. And similarly, so this is the third line, P total. P total is equal to P1 plus P2. And similarly, P total versus X2. P total versus X2 also give a linear line. Linear line. And the minimum value of P total is P01. So this is the minimum value and this one is the maximum value for P total. The minimum value of P total is P1 naught. So this one is the P1 naught. It is a P1 naught. And the maximum value of P total is P2 naught. And here we can conclude that the component 1 is a less volatile. The component 1 is less volatile than the component 2, because the component 1 pure vapor pressure is less than the component 2 pure vapor pressure. So P1 naught is less than the P2 naught. And let us assume that in the gas phase, the mole fractions are Y1 is the mole fraction of component 1, and Y2 is the mole fraction of component 2 in the gas phase. In liquid phase, the component 1 mole fraction is X1 and the component 2 mole fraction is X2. In gas phase, the component 1 mole fraction is Y1 and the component 2 mole fraction is Y2. And according to Dalton's law, the partial pressures P1 is equal to Y1 P total and P2 is equal to Y2 P total and Pi is equal to Yi P total. So this is the vapor pressure of liquid solutions, liquid in liquid solutions. So let us do one problem. The problem is vapor pressure of chloroform. The chloroform formula CHCl3 and dichloromethane CH2Cl2 at 298 Kelvin or 200 millimeter of Hg. So this is the vapor pressure and 415 mm of Hg, 200 vapor pressure of CHCl3 and 415 vapor pressure of dichloromethane. The first one, calculate the vapor pressure of the solution prepared by mixing of 25.5 grams of chloroform and 40 grams of CH2Cl2 at 298 Kelvin. And the second question, mole fraction of each components. So there are two sub questions. In first question we have to find out the total pressure, and in second question we have to find out the mole fraction of each component in vapor phase. This is the vapor pressure of chloroform, means the pure component vapor pressure, pure component represented by naught. So P01, first component vapor pressure 200 mm of Hg, and second component CH2Cl2 vapor pressure is, that is the pure vapor pressure, that is 415 mm of Hg, 415. And next to So the first component weight is 25.5 grams. So CHCl3 25.5 grams, and second component weight is 40 grams. So second component CH2Cl2 40 grams. And let me take that molar mass of CHCl3. So carbon atomic weight 12 into 1 carbon and 1 hydrogen, 1 into 1, plus the chlorine 35.5 into how many chlorines? 3 chlorines into 3, so is equal to, we will get 119.5 grams per mole. This is the molar mass of chloroform. And molar mass of CH2Cl3, 1 carbon 12 into 1 plus 2 hydrogens 1 into 2 plus 2 chlorines 35.5 into 2 is equal to 85 grams per mole. So this is molar mass of CH2Cl2. So here moles of CHCl3, we have to find out that moles. So moles of CHCl3, for CHCl3 moles, molar mass 119.5 equal to 1 mole. And we have how many grams? 25.5 grams. So 25.5 grams equal to how many moles? So cross multiplication, 25.5 into 1 divided by 119.5 is equal to, if you do this calculation, we will get 0.213 moles. So 25.5 grams of CHCl3 equal to how many moles? 0.213 moles. And next to moles of CH2Cl2. So here CH2Cl2, how many grams? 40 grams. So here molar mass of CH2Cl2 85 equal to 1 mole, and 40 grams equal to how many moles? Cross multiplication, 40 into 1 divided by 85 is equal to, if you do that calculation, we will get 0.47 moles. Now total moles, number of moles equal to 0.213 CHCl3 moles plus 0.47 CH2Cl2 moles is equal to 0.683 moles. Now we have to find out that mole fraction. So mole fraction of CHCl3 is equal to mole fraction of CHCl3, number of moles of CHCl3. How many moles of CHCl3? 0.213. Total number of moles 0.683 is equal to, if you do this calculation, we will get 0.312. The mole fraction of CHCl3 0.312. And we know that formula, sum of mole fractions is unity. So mole fraction of CHCl3 plus mole fraction of CH2Cl2 is equal to unity. So we know that mole fraction of this CHCl3, how much? 0.312. So then mole fraction of CH2Cl2 is equal to 1 minus mole fraction of CHCl3 is equal to 1 minus how much of this value? 0.312. Then we will get that mole fraction of CH2Cl2 is equal to, if you do this calculation, we will get 0.688. So sum of mole fraction is unity. 0.312 plus 0.688 equal to 1. Then we have to find out that total pressure. So we have that formula P total is equal to P01 plus P02 minus P01 into X2 is equal to, so here P01 200 and P02 415. So P01 200 plus into P02 415 minus P01 200 into X2 means mole fraction of component 2. Component 2 mole fraction 0.688. 0.688. So if you do that calculation, 200 and plus 415 minus 200, 215 into 0.688 is equal to, we will get 200 plus 147.92 and is equal to 347.92 mmHg. So this is the P total. First sub question over. Next, second sub question. Mole fractions of each component in vapor phase. So second one, we have to find out that mole fraction in vapor phase. Each component mole fraction in vapor phase. So before that, I'm going to find out that mole fraction in liquid phase also. So here in liquid phase, so we know that formula P is equal to P naught X. So here P, the first component CHCl3 is equal to P naught CHCl3 into X. So here P is equal to partial pressure and P naught is equal to pure component vapor pressure. So vapor pressure of pure component means before mixing with other component, and X is equal to mole fraction in liquid phase. So PCHCl3 is equal to P naught. P naught how much? The first component P naught 200. So 200 into X, mole fraction of chloroform. Mole fraction of chloroform we got in first sub question mole fraction of chloroform 0.312. 0.312. So let me take that 0.312. 0.312 is equal to, if you do this calculation, you will get 62.4 mmHg. So this is the partial pressure in liquid phase of first component. And second component, PCH2Cl2 is equal to, and P naught CH2Cl2 into X. So PCH2Cl2 is equal to P naught. P naught, second component, means P naught 2. So here P naught to 415. P naught to 415. So 415 into X, mole fraction of second component CH2Cl2. That second component mole fraction is 0.688. So let me take that mole fraction, 0.688. So if you do this calculation, we will get 285.5 mmHg. So this is the partial pressure of chloroform, and this one is the partial pressure of CH2Cl2 in liquid phase. But actually we have to find out in vapor phase. So here in vapor phase, P is equal to, here Y. Y is the mole fraction of component in vapor phase into P total. P total. Already we got that formulas. P1 is equal to Y1 P total, P2 is equal to Y2 P total. P1 is equal to Y1 P total. So we need that Y1, first component CHCl3 is equal to P1 by P total. So this is the into. So P1 means chloroform, PCHCl3 divided by P total is equal to partial pressure of chloroform. Partial pressure of chloroform 62.4. 62.4 divided by P total. So that P total is 347.9, 0.18. And for second component Y2 means CH2Cl2 is equal to PCH2Cl2 partial pressure divided by P total is equal to partial pressure of that CH2Cl2 is 285.5 divided by P total 347.9 is equal to, we will get 0.82, or we can find out that second mole fraction. We can find out that second component mole fraction. We know that sum of mole fractions is equal to unity. So YCHCl3 plus YCH2Cl2 mole fractions in vapor phase is equal to 1. So we know that mole fraction of YCH2Cl2 is equal to 1 minus YCHCl3. So we got that YCHCl3 0.18. So YCH2Cl2 is equal to 1 minus 0.18 is equal to, we will get the same value 0.82. Means we can find out that second component mole fraction in this way also. So the P total is equal to 347.92 mm of Hg. The first component mole fraction in vapor phase 0.18 and second component mole fraction in vapor phase is 0.82.